So how do we measure how big a brain is, anyway? We saw that Broca did it by measuring the volume of the skull and by weighing it. So that's two ways. But these days we've got better knowledge of how the brain is structured. Maybe we can count the number of neurons in the brain, as the people who were looking at the brains of hydrocephalics did. Maybe we can just count different sorts of neurons. Maybe we count the neurons and not the glial cells. Because we saw that when the brain was compressed in hydrocephalus, it was the glial cells that tended to be sacrificed rather than the neurons. Or maybe we can use some sort of imaging techniques to measure the sizes of different important areas of the brain. The bits that are to do with particular functions. Maybe there's a bit of the brain that does intelligence and we can isolate that. So that's what all of these different studies, they're going to differ in the way that they measure the brain. So they can come up with different results. And also we need to know, well, what do you mean by intelligence? Broca did it just by assuming differences in intelligence between men and women and different races, and between superior men and ordinary ones. These days, we're more likely to use an intelligence test to be a bit more objective, and here's an example of the sorts of intelligence tests. This is called Raven's matrices, where you have a grid of a 3x3 grid of 9 shapes with one missing. And you've got to work out which of the shapes at the bottom, which of those 8 shapes in that lozenge outline, fits in the hole to complete the pattern. And it's an abstract reasoning task. It's an analogical task. Can you work out which is the correct shape? This is supposed to be a measure of G, a general intelligence factor that psychologists have arrived at because it's a correlation between all sorts of different ability tests. They exhibit what's called positive manifold. If you're clever at one, good at one, you seem to be good at the others. All of these tests seem to have a positive relationship with each other. Well, Raven's matrices is a rather pure way of getting at this G factor. Uncontaminated by verbal ability, by knowledge, by training. And the way Raven's matrices work is it's simply a test, how many of these can you solve in a given time? The faster you are at it, the more you solve. And if we plot out the number that you solve, we will get a distribution. Now, we may not get this famous curve, the normal distribution, that was the title of Herrnstein and Murray's book, The Bell Curve. It's called the bell curve because it looks a bit like a bell with these flared ends. Intelligence, IQ, is normally distributed simply because we make it so. It's another assumption. Lots of things in the world that we can measure are normally distributed because they're made up of lots of little components, each with its own variation. And when you add all of these things up, lots of infinitesimal contributions to something, it's very rare that they're all going away from the general mean in one direction or the other, and so you tend to get scores clumping around this middle bit with a probability distribution fading away on either side. So that suggests that intelligence, if it's normally distributed, is made up of lots and lots of little different things. So it's unlikely to have one cause. So that's an assumption, though. We're making intelligence normally distributed. We don't get a normal distribution out of the test, out of Raven's matrices. We might find that half of the people have got 10 right in 3 minutes, and the next quarter have got 15 right, and the last quarter have got 25 right. They might be so good at it they can whiz through them. we didn't get a nice normal curve. So what we do is we scale our results to fit a normal distribution. We come up with a table of norms that says if you have got 10, your intelligence is bang on the mean, it's 100. If you've got 15 right, well, you're a bit better, you're 110. If you've got 25 right, you're 115. Moving slightly down that curve. Not a linear relationship between our score on the test and the intelligence score. It's simply scaled to produce our expectation, our theoretical assumption that intelligence is normally distributed. So we don't know that the bell curve is actually true or not. We've made our tests produce a normal distribution for intelligence. And the way the normal distribution works is that 68% of the people in the population, if we gave them this test, would score between 80 and 115 in IQ. That's one standard deviation above or below the mean. So it's 15 points either side of the mean. That would encompass just over 2/3 of the population. If we go out to 2 standard deviations, so we're going 30 points either side of the mean, from 70 to 130, then we're going to have 980 out of 1,000, or 98% of people within there. So almost all of the population will score within 2 standard deviations of the mean. We can go even further. We go back to 3 standard deviations, we would get 999 in 1,000. Only one person in 1,000 would score more than 145 on an intelligence test, or less than 55. But that's simply because we've designed the tests that way to produce that result, not because there's anything necessarily inherent in them. Really, all these tests are doing is going to be rank ordering people from better to worse. We impose the normal distribution on the results.